Seen how we can use equations to find the energy stored in an elastic material or the work done by an elastic material. Yeah, we have done that. Now we want to see how we can actually find the energy stored in an elastic material or the work done by an elastic material using what? Using graph. So join me. Let's do this part 7 of elasticity. Finding elastic potential energy from what? From graph. Okay. Now the graph we normally draw is the graph of force against what? Against extension. So the elastic potential energy can be obtained graphically from the force extension word graph or curve. So the elastic potential energy. Remember we said that the elastic potential energy is the work done by an elastic material or the energy stored in an elastic material. So the elastic potential energy can be obtained graphically using the force extension graph or curve. So when you draw the graph of force against what? Extension, you can actually get the what? Get the elastic potential energy from the graph. Yeah, remember the graph that you are going to use is the force versus what? Extension. Force extension graph or force extension curve. Now, so how do we get this elastic potential energy? We have seen where to get it, right? We say we use what? We use the force extension graph. So when I have a force extension graph, how am I going to use a force extension graph to do what? Obtain the elastic potential energy. Remember, it is the force extension graph, no other graph. It is the force what? Extension graph. So if you know what to use, the next thing is how to use it. How can I use the force extension graph to obtain the what? The elastic potential energy. So how? The area under the force extension graph or curve is equal to the elastic potential energy. It's equal to the elastic potential energy. So the area under the force extension graph or curve is equal to the elastic potential energy. Therefore, to find the elastic potential energy, we do the following. One, take note of the curve. Take note of the curve. Taking note of the curve means you have to ascertain that that curve is a force extension curve. Number 2, take note of the shape under the area, the shape of the area under the graph or curve, under the graph or curve. So when you have the graph, note the shape of the area. Remember, we have said the area under the curve or under the graph is your elastic potential energy. So when you take note of the graph, check the nature, take note of the area and the shape of that what? The area under that graph. Then use a suitable formula for finding the area to calculate the the calculated area is the elastic potential energy. So these 3 steps are enough. Now we need to note this, very important. We have been talking about the shape of the area. There are possible shapes of the area that we can obtain. So note the possible shapes of the area under the curve include triangle, rectangle, and trapezium. This implies that students must know the formula for finding areas of triangle, rectangle, and what? Trapezium. So I'm going to give these areas. Now, let's give the areas. We are still on finding graphical approach to this. So let's give the area. So area of a triangle is half base times height. Area of a rectangle is length times width. Then area of a trapezium is equal to half x plus y times the height of the trapezium. So where we can say that B here now represents base of the triangle, H represents the height of the triangle, L represents length of rectangle, W represents width of the rectangle, then X and Y are the opposite parallel sides of the trapezium, and the uppercase letter H represents the height of the trapezium. Okay, now we're going to see the first extension curve or graph in 3 different ways so that we can relate. But before that, let's make another important statement. You see that B, it is important to state that B, H, L, W, X, Y, and H are force or extension terms, since they can be obtained from the force axis or extension axis. Okay, now let's explain this further. If I have this graph, this is the graph of force in Newton and extension in meters. Let's say it's in meters. Now, if you draw this graph, let's say that the graph is like this, and they say, what is the work done? What is the work done, or the elastic potential energy, or the energy stored in the elastic material? This is where this graph ended. So this is the end of the graph. This area under this graph, because see the graph here, is a triangle. Now you notice that from here to here is the base, and from here to here is the what? Height. Do you get that? Do you notice that this height, if I want to read it, I will read it from first. From here to here will be from here to here, which is on the first axis. If I want to get the value of the base, I'm going to get the value from the what? Extension axis. Do you see that now? So that's why we say that this B, L, H, and so on, they are either force or what? Or extension. That's what we say. So here now, this is height representing the force here. So the base is an extension. So if you now say half BH, you can get the area of this triangle, and this area of this triangle, the area of this triangle becomes the what? The work done. Supposing the shape under the graph is a rectangle. Let's say that upon drawing the graph, that will have this extension in meter, force in Newton. Let's say I have this, and after drawing the graph, I have something like this. Now you notice that this is a rectangle now. The whole of this is a rectangle. It's a rectangle. So this becomes the length. This becomes the width. So from here to here is still this length. So if I want to get L, is from the extension. It is the value of the extension that is equal to the length. If I want to get the width from here to here, is from here to here, which is the force. So it is the value of the force that corresponds to the what? To the width. So if I get the length from the extension axis, get the width, then multiply, I will get the work done by the elastic material or the elastic potential energy. It's still possible that we can have a trapezium. Yes, before we end. It's still possible that we can have a trapezium. It's possible that we'll have this. So force in Newton and extension in cm. It's possible that we can have something like this. If you complete this now, this becomes what? A trapezium. Yeah, it's a trapezium, the whole of this area. This side and this side are the two parallel sides and opposite side of the wall of trapezium. So this is the height. This is x and the y. You see it? So using this formula now, x, y, h. Now you see that your y is from here to here. You see that? From here to here is your y. And your x is from here to here. So both of them are from the extension axis, right? Extension in meters here or in cm, whichever one. But we need to make the unit consistent. Y from here to here is from here to here, which is from the first axis. So once you see a graph and you are required to use the graph to obtain the energy stored in an elastic material or the elastic potential energy, you must know the shape of the graph so that you know whether to use this, or this in calculating that area. So 3 steps. Take note of the graph. Check very well whether it is a force extension graph. If it is a force extension graph, it is suitable for finding the energy stored in an elastic material. The next thing is to take the note of the area under that under that graph and know the shape of that area. Is it a rectangle? Is it a triangle? Is it a trapezium? When you establish that it's a triangle or rectangle or trapezium, you now have the expression to use. Properly identify the terms for each of the areas given here. Once you identify that, then you can now solve your problem by substituting. Wow. Part 7 of elasticity is over. We are going to head over to part 8. And in part 8, we are going to start looking at the basic terms in what? In elasticity. Remember, we still have force extension graph to treat, and we still have stress strain graph to look at. So by the time we look at the basic terms, we are going to look at stress, we're going to look at strain, we're going to look at young modulus for SSCE and that's WASI and UTME. We are up to young modulus is okay, but I may add bulk modulus. I may just explain it also. Yeah, I may add bulk modulus. And immediately after looking at these 4 terms, we will now look at the force extension graph and the significances of force extension graph, and also the stress strain graph and its significances. Thank you for watching our video. I'm still your brother, your friend, and your humble tutor. Engineer Ike is still my name. Make sure you score 300 and above in your UTME, and also make sure that you excel in your WASI. I love you.